Okay, let's take a look at the problem with the pumpkin. Here's the solution for this one. Let's take a look at the basic ideas. Okay, hey, we have a pumpkin here, person attempting to pull it to the left. It looks like I've already made the interaction diagram. Let's see what other information we have. Scrolling down here. Okay, so we also have on our position versus time graph, we see that it's at a position further to the right and then moves back to the left. Other things I see here is that because the position versus time graph is straight, that's going to be at a constant velocity. This should give us enough information to put this all together. Right. Hey, why don't we, as long as we're in this place, let's go ahead and make our velocity graph. So my velocity is my change of position over time. Hey, so I started at a position of 90 meters and I went backward to a position of 30 meters. So I had to go backward, or let's see, a negative 30 meters. How long did this take me? From 0 to 20 seconds. So it took me 20 seconds. So my velocity, you can see, is minus 3 meters per second. Let's go ahead and put this on the graph. So minus 3 meters per second constant velocity. I've labeled the axes with units, and that would end up being changed my color here just so you can see a little bit better. Okay. That shows minus 3 meters per second. Scroll back up to the top of the page here. Okay. Hey, so we have some additional information we can now figure in here. Okay. Hey, relationship parameters. Is it at rest? Certainly not, because we see that it was moving from that graph. Constant velocity? Yes. Say the same velocity all the way through. And because our velocity is constant, our net force is equal to 0, so our forces are balanced, yes. From our interaction diagram, let's construct our force diagram. And so I go around here, let's see, what do I have? I have gravity here. I know that's acting down. Force of gravity on the pumpkin from the earth. I have a normal force. I see my forces are balanced, so forces up are going to need to equal forces down. I'll make this the same length. Force normal on the pumpkin from the ground. Let's go around here. I get tension that'll act to the left. Force of tension on the pumpkin from, I'll call it the rope. It looks like I have the interactions between the pumpkin and the rope. And then again, because we're balanced, we're moving, but we're balanced, we're going to have an equal force to the right from the friction. Force of friction on the pumpkin from the ground. Let's indicate that those are similar. Okay, at this point, I'm just going to make up some values for the force diagram. As long as they're showing balance, they could be really any value. But I'm going to assume that, hey, the pumpkin, this is a pretty big pumpkin. It has a weight of 40 newtons. That's about 800 pounds. Sorry, that's about 80 pounds. Be a really big pumpkin. It was 400 newtons there. Person over here looks pretty strong. So they can pull at 250 newtons, and we know that the friction also needs to be 250 newtons. These values here are just made up. You know, whatever value you had is just fine, but as long as they show balanced. So I'll create some event or scenario that matches all this. All right, so I came up with this scenario. I drag a giant pumpkin, 400 newtons, across the ground to the left. I know left because the position was decreasing at a constant velocity. Know that because the position versus time graph was straight, 3 meters per second. That's what we've calculated the velocity as. And then with a force of 250 newtons. And that value was just made up, but I know I was dragging it to the left. And let's take a look at that further question at the bottom. Hey, what direction is the friction acting on the man? Friction between the figure and the ground. Okay, so just a quick look at that. That pumpkin, that the friction is pulling the pumpkin to the left. Therefore, that did I say that? Sorry. Tension is pulling the pumpkin to the left. Therefore, that tension must be to the right on this figure. To balance that, the friction must be to the left. So we know that that's going to be to the left. So putting it all together, here's that the final answer.